Hello one, hello all. Welcome to another episode together. Today we're going to go through the resistance lab. Of course, with our setup right now, unfortunately you can't do it in person. We'll have to end up doing this virtually. But I still want to tell you a bit of background of what resistors are and the properties that they should exhibit. So I'm going to first switch off to a different camera view. And just for scale, here is my calculator. And what else can I click on? I think I can click on this button here. Where's the button? Wrong button. There you go. All right, just so you can see a large addition of what's going on. So here's my calculator for reference. And if you're wondering what a resistor is, here's a resistor. All right, so if you take electronics class, that's the one that you're used to. And if you look carefully, yes, it is color coded. I know my lighting's not at its best, but there's usually color bands, and the color bands will tell you the resistance. Now in this model here, it's not color coded, so yeah, it's not a trickery of the eyes. Instead, if you look very carefully, it's numerically etched on, probably with a laser. All right, and that's the resistance of that resistor. Normal resistors will be color coded like this guy over here. All right, and resistors, they do come in different sizes. These are the ones that most people are used to. They're quarter watt, I believe. And then you can upgrade to the 1 watt or 2 watt. I don't even know what that is. And if you want it even bigger, I think this is the biggest one in my collection right now, the 5 watt. And they do come in larger sizes. And also they do come in smaller sizes. For example, here's a flat pack of a bunch of resistors, and you can see that they're smaller than the size of my nail. And these are the ones that you commonly find in modern day circuits. All right, so they do come in different sizes. And yes, we do prefer smaller ones for two things. A, they're smaller, so you can build smaller devices. And B, in real life, we don't want resistors in our circuit. One of the problems about resistors is that, as implied, they inhibit current flow. And if they inhibit current flow, well, that means that that energy needs to be dissipated somewhere. And that energy is dissipated in the form of heat. And that's why resistors come in different sizes. Some can dissipate very little heat, like a quarter watt. Others can handle 1 or 2 watts, like this size here, and others can handle 5 watts. As for these miniature ones, they can't handle much heat at all, but then again, you don't want to release things as heat, because last thing you want is for a calculator to heat up, all right, for one of two things. You don't want it to A, explode, and B, heat is wasted electricity, and you don't want that happening. So in modern technology, we're really moving away from resistors, but understanding the foundations of how resistors behave is the beginning of understanding electronics, and that's why we always start with this. Okay, so these are known as resistors. Even more specifically so, they're known as ohmic resistors, named in honor of George Ohm, who discovered there are certain elements out there, or compounds, that exhibit ohmic properties. What exactly is an ohmic property? Well, it's one where as you increase the voltage, you expect the current to increase at the same rate. In other words, with the formula, V is equal to IR, or if you want to find out the ohmic properties of a substance, then resistance is equal to the measurable voltage divided by the measurable current. And if this trend over here remains consistent regardless of the voltage, then you have something that's ohmic. In other words, as the voltage goes up, the current will go up in such a way that this value remains the same value. And that's the objective of this lab, all right, to see if resistors abide by this property over here. Okay, so a bit of calculation background. One of the other things to add to this lab over here is that we want to express our measurements using the correct degree of certainty or precision. And there are ways to describe certainty and precision on a graph. So let's go through that exercise first. What am I showing here? All measurements here have to have a measurable value and uncertainty. You can see in this diagram here, this is the first generation iPod, and this author over here did not describe the uncertainty. I won't be surprised if the uncertainty is plus minus 0.0 some number over here. Looking at the values here of 4 and 6, it could be plus minus 0.01, or it could be something less than that. Okay, so the uncertainty is probably going to be less than 0.01, some value like that. Okay, so all measurements have to have an uncertainty, and you probably also want to include units so the reader knows what you're talking about. Normally in these type of diagrams, you'll have a box down on the bottom right-hand side, and it'll describe the author as well as the appropriate scales. Okay, and yeah, one last cool thing is if you take a look at this curve over here, yes, this is the famous Fibonacci curve. And Steve Jobs, I guess he was so obsessed with regards to perfection. If the most beautiful objects resemble that of the Fibonacci curve, well, take a look at that. Isn't that beautiful? Okay, enough of that. Okay, so how do you deal with creating graphs that also include uncertainty. All right. So take a look at these data points listed right over, where is it? Right over here. Okay. So each of these data points are not exact. They have errors associated with it. And that's the truth with all sorts of measurements. There's always an error. So if you need to factor in errors in your measurement, then you'll want to include uncertainty bars. So let's say that the error in this case over here has an uncertainty of plus minus 2 units. Okay, in accordance to the scale over here, where we take it that the scale here is 1 unit for every grid line. So to tell the reader that vertically we have an error of as much as 2 units, we'd end up extending these whiskers. And these whiskers will tell the reader that even though I may have gotten this measurement over here, it could have been as high as that value here or as low as that value down there. Okay. And the same is also true with regards to the next measurement. It could be as high as this measurement up here or as low as down there. And we carry that idea through with the rest of it. And when we go through drawing our line of best fit, it should really fit within your error margin. You can also treat this the same in the horizontal dimension as well. I'll use the same uncertainty. If your uncertainty is plus minus whatever these 2 units are, then yeah, you have some of these TIE fighters around. And again, your line of best fit needs to fit into here. One thing to point out, however, is that when your errors are rather large, we can't really tell if this represents that of a linear correlation or that possibly of a quadratic, because they both fall into this trend here. And that's why you want to carry as many data points as possible. So when you conduct your lab, you want to have as little as 7 data points, ideally as many as 10 data points, that we can confidently determine whether the relationship is linear, quadratic, square root, inverse, inverse square, so on and so forth. All right, so you want to have as many data points as possible. Now, sometimes when you do your lab measurements, your values are very certain. And if it has a high degree of certainty, then it's hard to describe, but with a bunch of these vertical whiskers and horizontal whiskers to tell the reader what it is, because you can imagine the graph being very ugly looking when you do something crazy like this. All right, there's just too much going on. So if your uncertainties are really small, what you'll do instead is that after you dotted out all your dots of your measurements, you'll draw a circle around it to tell the reader that there is an error in your measurement, but the error is somewhere within that uncertainty circle. And when you conduct this lab, especially using the virtual version, you'll notice that your errors are typically this small to begin with. All right. So when you conduct your lab and you show your lab results, it should look something more like the next slide. So this is the expected outcome. Now, with this student over here, I found this as a version online. You can see there's a lot of deviation and a lot of outliers in the student's measurements, which probably means that the student had an error uncertainty that which was much greater than anticipated. So truthfully, this lab probably should have been drawn using these whisker lines, and the student should have been more careful with how he or she gathered the information. Because in truth, if the person gathered the data correctly, you'll see that the line of best fit will pass through all of the circles. Okay, so the next thing is, what exactly do we plot here? Remember that whenever you plot a graph, you'll always label it as the dependent variable versus the independent variable. So yes, this is the experimental resistance of a known resistor, but this is also can be called as a voltage versus current graph. Okay, remember that the first thing that you label out is always going to be on your dependent axis or your quote unquote y-axis. And the second statement that's listed in your title always describes your independent axis each and every time. So if you look at the instructions, you're supposed to produce a voltage versus current graph. All right, so that is the expected outcome of this diagram here. And you'll notice that these dots over here, they more or less show a linear correlation. All right. So if they show a linear correlation, then that does describe something that exhibits an ohmic property, because that's what George Ohm stated. Anything that has an ohmic property will have this linear correlation between voltage and current. All right. So voltage and current will be correlated. How are they correlated? Well, V is equal to I times the constant of R. In other words, when you solve for R, that is a relationship between the voltage over the current. So that's the next thing you're going to do with regards to this lab over here. You're going to look at the relationship of this slope. Okay, so after you've dotted out all your points, after you've drawn your line of best fit, you're going to choose two separate two separate points on the line of best fit itself. Please do not use the values that you've initially received, because if you use those 2 points there, you'll notice that your slope does not match up with the final answer. It'll clearly deviate away from it if you use any of those 2 points. As you're trying to average out your errors, you want to choose points on your curve, and you want to choose two far away extremes. You can imagine if you choose 2 points that are close to each other, then you're effectively subtracting 31 from 30, which will give you a delta of 1. As I mentioned, if you only show one significant figure, you could be up to 100% off in your answer. All right, so you don't want that to be the reason why your answers are off because you chose 2 points that are close together. If you choose points that are very far away, such as, I don't know, 56.5 versus 11.2, well, now you're dealing with a 3 significant number, subtract the 3 significant number, and there's a good chance you're going to still have 3 significant figures at the end when you deal with precision. Okay, so that's why you want to choose values that are far away when you measure out your slope. That way you have more sig fig to deal with and your errors will decrease. I think I have some sample calculations over here just to show you what I did in my version here. All right, so we chose a value all the way up here of 56.5 volts, and we're going to compare it with 10.0 volts. Now, they have their own uncertainties in their measurements. When you're looking at the scale over here, as this graph is very cleanly, even though it shows the minor divisions, it's still hard to divide the minor divisions by 10 units. So that's why my uncertainty, my voltage is plus minus 0.5 volts. Okay, so there's uncertainties in even my estimations by looking at where the points are. That is true both horizontally as well as, both vertically as it is in the horizontal dimension. Okay, so in the horizontal dimension, I have an uncertainty as well. If you look at my grid divisions over here of 0.1 all the way up to 0.2, if I'm uncertain by just half of these grid lines here, that is equivalent to 0.005 amperes. So that's where I got my uncertainties from. It's the uncertainties from the graph itself, from analyzing the graph. All right, very similar to your power lab. What you want to deal with first is that you want to first deal with the numerator. Since it's subtraction, then 56 subtract 10 will give you 46.5 volts. And your error of your uncertainty will always get worse. So 0.5 volts plus 0.5 volts will give you 1.0 volts of uncertainty. And we treat the same thing with the denominator. And as you can see, whenever you subtract a very big number from a very small number, you get an uncertainty, which is still 3 sig fig. That's why you want to choose extreme numbers, not numbers that are too close to each other. Okay. And as for your error analysis, again, whenever you add or subtract, your errors always increase. So 0.005 plus 0.005 will give you an uncertainty of plus minus 0.01 amperes. All right. Next step is that we're going to divide these two. And anytime that you divide two measurements, you need to convert your absolute uncertainty into a percentage uncertainty or a relative uncertainty. So you're going to do 1 volt divided by 46.5 volts multiplied by 100%, and that will give you 2.15%. Make sure you show your work when you do this. All right. So show work. The same is also true with regards to converting from 0.01 amperes into a percentage. Make sure you show your work. That's not shown here in the PowerPoint. 46.5 divided by 0.765 will give you 60.78 ohms. And again, with your errors can only increase. So you're going to add your errors. Even though you're dividing, you're still adding 2.15 with your 1.31. So that gives you a 3.46% error. Now, 3.46% of 60.78 works out to around a 2 ohm error. Okay. Now, with a 2 ohm error, again, we only want to show our errors to one significant figure because you don't know your errors to 3 sig fig. If you did, then that means you measured everything very precisely, and you should precisely know your final answer. Okay. So that's why your uncertainty is only going to be one significant figure because it is an average error. So if your average error is going to be around 2 ohms, then we don't care about these digits over here. We're going to round to the nearest whole. So our final answer, at least in our current setup, it should have been 61 ohms plus minus 2 ohms of an error. Again, what we're doing over here is that we're producing a voltage versus current graph. And as long as it exhibits a linear property, the slope of this graph over here tells us the object's corresponding resistance. And that's our answer for this particular lab. Any questions before I leave you off to the races? Okay, so I do have to modify things when we're doing this virtually. In real life, you will be using a proper multimeter. All right, and with a proper multimeter, remember that your voltmeter needs to be connected in parallel. Okay? And we've talked about this before. We could use more voltmeters to measure out the potential drop. And according to Kirchhoff's voltage law, 4 volts subtract 1.4 volts should tell us the potential difference of the third load, or the second load, sorry, the second load. In this case, the second load is at 2.6 volts. So 2.6 plus 1.4 will give us 4 volts. Voltmeters are very hard to destroy. You can wire it however you like, and as long as you're dealing with less than 1,000 volts, you'll probably survive. An ammeter, on the other hand, as I mentioned, an ammeter internally behaves as a short circuit. So internally, there's a shunt resistor inside, giving it a resistance that's very close to 0 ohms. So whenever you use an ammeter, you need to make sure that you break the circuit. If you don't break the circuit, like in the setup over here, well, as you may know, current likes to go through the path of least resistance. And since the ammeter usually has a resistance that's around 1 ohm or less internally, it'll go through the wire first before the ohm meter. So you're not going to measure anything like this. You'll need to break the circuit to measure current. Of course, do not connect it together in parallel, because if you connect it in parallel, well, the light bulb here has a known resistance, probably 10 ohms or more. And since the ammeter has an internal resistance of less than 1 ohm, current will flow through like crazy through the ohm meter, or sorry, through the ammeter, and you end up with a Minecraft explosion. All right, so please do not connect ammeters in parallel. Always connect them in series. That way you can get the proper measurement of current. Now, we don't have to include a third ammeter here, but I think that after you've mastered Kirchhoff's current law, you know that if you have 2 amperes going in, if 1.4 amperes goes down, then you'll have about 0.6 amperes traveling across through the second branch. And that will only show up the moment that you complete the circuit. And there's your answer. Okay, you're dealing with everything virtually, so there's no chance in damaging any of these ammeters at all. But this is how you'd hook them up if you owned an ammeter. Okay, always connect ammeters in series. There's a real voltmeter, and yep, here are the corresponding setups for it. All right, so to switch between volts and current, you'll often take your leads and you'll reconnect them in different positions, because internally the meter has to be different. With a voltmeter, its internal resistance is close to infinity. So in other words, it needs to behave as if it's not part of the circuit. It's just there just to hover off and just look and see what the potential drop is. All right, so that's why it's going to be wired a certain way internally, and that's why you need to plug it into certain plugs. As an ammeter, it needs to behave as a short circuit. So if you take apart and dissect an ammeter, you'll notice that inside there's either a piece of metal or a rather large resistor, so that it can allow maximum current to go through. In fact, it cheats. What an ammeter really does is that it measures the potential drop across that little shunt. And if it knows the resistance of that shunt and the potential drop across it, well, V divided by R gives you I. So that's how all ammeters cheat and work the way they do. An ammeter really is a voltmeter in disguise. Right? So as long as you hook up everything properly in your lab, it should work out in real life, and same as in the virtual world. So let me just show you how to solve this lab in the virtual world. I'm very grateful for whoever this guy is. He ended up taking all these old animations on the internet and putting it all together on his own website. And I think he ended up creating his own simulation for resistance as well. So please follow through these instructions over here when you're conducting the virtual lab. All right. So let's go through the basics of this virtual lab that you'll be conducting at home. You'll be going onto this website over here. And is there a full screen option? I don't think there is one here, so I'm just going to cheat and just zoom in a little bit more. Okay, now his simulation is fairly advanced. It not only does it do resistors, it can handle capacitors and inductors as well, and show that, yes, in real life, electricity can behave as a wave. All right, so there's more to learn in electricity. But we always start off with the basics, and the first basics is dealing with resistors and Ohm's law. All right, so you can play with this circuit over here just to see that, you know, how you play with different resistors in a circuit, how it can have an impact in your circuit. You can see that there's a short circuit here on the right-hand side, and that's why the current didn't flow through the 600 ohm and 200 ohm resistor. For our lab, you can either take the circuit here and start deleting away by selecting, highlighting, and deleting, or you can just go right into, I believe it's Ohm's law. Okay. Now this circuit is still too complicated, so you're going to select the right-hand side and hit the delete key on your keyboard and simplify it. And if you want to clean it up even more by bringing it over here and deleting this branch here, whoops, Control Z, by the way, allows you to undo any of your mistakes. And there you go. Here is the simplified circuit, and this is all you really need for your lab. Okay. Now, to make things more unique for every student, what I need you to do is I need you to take the last 3 digits of your student number and input it as the resistance value. So you'll double click on the resistor. You may need to stop it first. And once you double click on the resistor, you'll type in the resistance value of, let's say, 1, 2, 3. I'm going to use this as our example. All right. Now, I know that you know the last 3 digits of your student number. All right. So I don't want you to cheat. Instead, I want you to go off and go to Options and click on Show Values to remove it. So let's pretend you did not know the resistance of your resistor. To keep things random so that every student has their own unique lab, this is the only way I can randomize it. Okay. And I hope that nobody here has 0, 0, 0. If you have the value of 0, 0, 0, then pick any 3 random digits that you want. Okay. So anyone who has 0, 0, 0, choose any random 3 digits. I'll let it slide for you. Okay. So it has to be non-zero for your values, and it's going to be left as a mystery. The next thing is that the 5 volts may not be enough, so you may need to bring it up to 10 volts. That way you have more numbers to play with. Could you leave it at 5 volts? You probably could. All right, and you can leave it at 5 volts, but for those that need that extra range, you may need to increase it up to 10 volts. As for the final answer for the current flowing through here, here is the simulated ammeter. So it's a piece of wire that's been activated to behave as an ammeter, and you can see that it's connected in series with the circuit. All right. Now you can run the circuit simulation, and you can change the voltage, and you can see that the current will be impacted by the input voltage. So what you need to do is I need you to choose 10 random points and produce a scatter plot with it. Now, if you know the keyboard shortcut on Windows, it's the window button and left key and booyah. Now I can shift this to the left, and I can also pull out Excel and Windows, arrow to the right, and it'll snap to the right. And now we can start collecting our data. Now this is a little bit too zoomed in, so I'm just going to zoom out so I can see the scrolling thing, so I can scroll it back and forth. And maybe just one more jump. That should be enough. All right, and I'm just going to have a random subset of values where I'm comparing between voltage and current. Now remember that voltage is my dependent value. All right, and your dependent value is your quote unquote Y value. All right, but whenever you plot out plots on Excel, it's always independent versus dependent. So your X value will be in your first column, and your Y value will be on your second column. So just watch out for that. Okay, your dependent value, which is a dependent, will be over here, and that's a measurement of your voltage. And your X value, or your independent value, will be over here, and that's your current. Now it's up to you to how you decide to measure and scale these out. For example, in this case over here, it's measured in milliamperes. So if you want to measure your current in milliamperes, you can. Just watch out that when you measure your slope, your X value is not in amperes, it's in milliamperes. So you need to divide by your answer by 1,000 for your current. Otherwise, you'll get the wrong answer. If you want to avoid that, then you may want to just convert into amperes in the first place. So that works out to 0.0446 amperes. And the voltage is 1.8 volts. Again, we're going to choose another random point over here, and I'm just randomly scaling it up and down. So 0.0293 amperes, 3.6 volts, and that's just by pure coincidence that I doubled it. And really, I can choose any voltage, and it doesn't have to be in linear order, although you probably want to collect it linearly. All right, so here's another example of 0.0081 milliamperes with a voltage of roughly 1.0 volts. One of the problems about the scale over here is that it's supposed to show 1.0, but the author did not show that next digit. So it accidentally makes it look like it's one significant figure, even though it's 2 significant figures. All right, so I'm just moving this voltage scale up and down randomly, and I'm collecting the data. So here I have 4.2 volts and a current of 0.0341 amperes. Choose a few more, such as 6.8 volts. Remember that my 6.8 volts is my dependent value, and it's based upon my current of 0.0553 milliamperes. Now, I know here's a weird thing. We did talk about our current as our independent variable, but you could see that according to the simulation software, our voltage is our independent variable. After all, we're changing the voltage and seeing the current change. I know that's one of the problems about our lab setup. All right, it's very expensive to find an ammeter where you can control the current. They do exist, but they're very expensive. Meanwhile, finding a lab bench power supply which can change the voltage alone, those are rather affordable. All right. So the reality is we're doing a slight little hack. We're modifying the voltage to see the current, but if this exhibits ohmic properties, you'll always have this correlation. In other words, every single time that you have a current of 55.3 milliamperes, if you had an ammeter power supply, you're going to have a voltage of 6.8 volts at the end. So we're kind of doing the lab in reverse, but we should expect the same results at the end. All right. So here's one more data point of 0.065 milliamperes for a voltage of 8 volts. And yeah, I'll just choose one more for kicks. Why not? 8.9. Why not? All right. So 8.9 volts, again, it's 2 significant figures for a voltage. And our current, as we can see, is 3 significant figures. So 0.0724 amperes. So we have a higher certainty for our current than we have for our voltage, at least in the simulation here. Okay, so our voltage uncertainty is probably plus minus 0.1 volts. I'll just write this down here for our reference. What is it? Quote, plus minus 0.1 volts. That will be our, or actually it's 0.05 volts for uncertainty in our Y dimension. The reason why it's 0.05 is that with voltmeters, they are calibrated in such a way that you always have an uncertainty that's half of your least significant digit. All right. So if this can estimate to the nearest tenth of a volt, then your uncertainty is going to be half of a tenth, or 5/100ths of a volt. And the same is also true with your current. If our current can be measured to the nearest tenth of a milliamp, then our uncertainty is going to be a very small uncertainty of plus minus 0.12345 amperes. Okay. So that'll be the uncertainty of the current. And that's something that you'll note in your notes, right? That your current, your uncertainty is going to be 5/10,000ths of an ampere, I believe, and your voltage is going to be 5/100ths. All right, now let's get on to our scatter plot. Our scatter plot only involves this data. And again, to properly plot out a scatter plot, your first column always has to be your independent axis. That's how it's always set up. All right, so since current is your independent axis, that's why it needs to be on the left column, and your dependent axis needs to be on the right column. We're going to select just the data points over here, and we're going to go and click on, let me just maximize this so we can see all the icons. We're going to click on the thing that looks like a bar graph over here. And the bar graph allows us to choose the selection of the type of graph we want to produce. We want to produce a scatter plot, and if you want your scatter plot to also include your data points, then you'll select this one over here. Now, what's the difference between these two over here? The one on the left averages it out and kind of creates a curve with it, and the one down below creates connect the dots. And as I said, you do not want to play connect the dots. You want to average it out. So even though this may not be the exact correct graph over here, you'll want to draw a line of best fit through these data points. So maybe you want to turn off all those points. Okay, so your graph looks like that. Now, for the purposes of this lab over here, I'm going to turn it on just so you can visually see that you do form this relationship. And yes, it should be a linear correlation, meaning that it does exhibit an ohmic relationship. All right. Now, when you plot out your graph, again, I want you to turn on all your minor grid divisions. So when you select on next, make sure that when you go to grid lines, that you emphasize both the major and minor grid lines. So that's where you activate it. You go to grid lines first, and then you activate it over here. As for the legend, as we only have one set of series, you don't need that. So you can delete that. And I think that's all you need to label here. You probably want to label out your X value right over here as current. And I've set it up as in amperes. And for your dependent axis, it's your voltage measured in volts. And our chart title is voltage versus current. What is on line 11 again? The line 11 is your uncertainty of your measurements, all right? Because with all your measurements, there's an uncertainty associated with it. And your uncertainty is always going to be half of your least significant digit. Okay, I'm going to create it as a new sheet just so I can maximize it so you can see the whole full-blown picture. And if you double-click on the background gray, you can remove that gray, which is area none right here, okay? Because we want it to be nice and clean. In fact, to clean this up even more, you may want to double-click on your minor grid divisions and convert it from a solid line into dotted lines, as it is minor grid divisions, and you'll rinse and repeat in the vertical dimensions as well. Okay, so that's how you can clean up your graph and make it very presentable to the reader. So you can see all the major grid divisions and the minor grid divisions. All right, and if you want to clean it up even more, maybe you want to adjust your scale so that it cleans it up nice and clean where our maximum value, let's say here, works out to 0.1. That's all. Okay, so you could adjust this as necessary so that your graph will be scaled accordingly where hopefully you have these major and minor grid division lines that more or less form closer to a box. All right, so you can still keep on editing this away so it looks more like a box than a rectangle. It doesn't have to be done, but it does make measuring slopes a whole lot easier. So maybe I need to try, I don't know, 0.13 here, just so that it resembles that more of a box, and I probably clicked on the wrong thing. All right, I'm not going to toy around with that. I'll just leave it at this. So again, you're going to be drawing a line of best fit on top of here. I know that I've cheated and I've activated this just so you can visually see it. Last thing you're going to do is you're going to measure the slope of this. All right, so you're going to be choosing 2 data points from here and working through it. To show you that, how about I make a new PowerPoint slide emphasizing that. So let's say that this is your collected data. And again, we're going to choose 2 extremes. Ideally, the extremes you want to choose are extremes that which pass through the crosshairs of your graph paper. All right. For example, right here. That way, we know that in our givens, what do we know? We know that our voltage, or our V2, if we measure it over here, is equal to 8.6 volts with an uncertainty. Because these grid lines are so close to each other, it's going to be half of that grid line uncertainty. So plus minus 0.05 volts. That's our V2. And as for our I2, well, that's nice and clean because we know that it's 0.07 volts and our uncertainty is going to be rather low. It's still going to be half of the least significant digit, so it's plus minus 0.05 amperes. Whoops, add another 0.05 amperes. Okay, so your uncertainty is always going to be half of the least significant digit. As for 0.07 amperes, that least significant digit is right over here, right? It's in the hundredths position. So half of a hundredths, or half of 0.01, if you divide that by 2, you get 0.005, and that's where I got the uncertainty over here. Okay, so your uncertainties, at least on a digital device or one where the graph paper is so thin and fine like this one, you're going to be estimating to the half of the grid divisions on the graph itself. Okay. All right, so that's my V2 and my I2. As for my V1, I1, I'm just trying to look for another point that passes through the grid lines. And the best I could see is right over here. Okay, so I can see that my V2 is at, it's closer to 1.2 volts. Again, my uncertainty is plus minus 0.05 volts because it's always going to be half of the least significant digit. Okay, if you look at the least significant digit over here, this is in the 10th position. And the 10th position divided by 2 will give you your 0.05 volts. All right, as for your corresponding I2 value right there, 0.01 amperes, we're going to play the same game, 0.005 amperes is our uncertainty. Okay, and what we're trying to do here is we're trying to measure the slope over here because our slope translates into our measurable resistance. All right, so our resistance here will be equivalent to that of our change in voltage over our change in current. So our resistance is equal to our delta V of 8.6 volts plus minus 0.05 volts, subtract 1.2 volts plus minus 0.05 volts. We're going to divide that by 0.07 amperes plus minus 0.0005 amperes. And I'm going to subtract that with 0.01 ampere plus minus 0.0005 amperes, close bracket. Again, at first, following the rules of BEDMAS, we deal with addition and subtraction first. So 8.6 minus 1.2 will give us 7.4 volts plus minus 0.1 volt. Remember, your errors, you always add. (0.07) subtract 0.01 will give us 0.08 amperes plus minus 0.001 ampere. Yeah. In fact, yeah, that's true. Is it? No, I said 0.08. Is that where my error came from? Okay, thank you for noticing that. That should be 0.06 because that's like really far away. Because remember, we cheated. We already know the answer is 1, 2, 3. So that's why I was surprised it was so far off. Okay, so 7.4. You know what? Let's fix up everything else. So thank you. I guess that's one of the benefits of being live. You get to see my mistakes in real time, and we can correct through those mistakes and get to our final answer. Here. And that's why my error is not 16%, but 1.66. And that makes more sense because I don't know how I had an error that high. Okay. That just suddenly skyrocketed. So 1.35 plus 1.667 will give me a 3% error, and that's a lot more reasonable. So 3.017% error. 3% of 123.33 gives us 3.72. So 123.33 ohms plus minus 3.72 ohms. Again, our uncertainty should only be 1 sig fig, so that's why that gets upgraded to 4 ohms. And as 4 ohms is rounded to the nearest whole, our final measurement should also be rounded to the nearest whole, so we'll stick to 123 ohms. And that would be our final answer for this lab. Okay, so if I give you a random resistor, which I would normally do in the classroom, and I tape it up, I'd have you do this exact lab. I'd have you increase the voltage, drop across the resistor, measure the current flow through it, do it another 6 or 7 more times, collect those table of values, draw this graph over here, measure the slope of the graph, and get to your answer. Now, remember, I cheated, and we said that we started off with 123. Well, here we go. It's 123 ohms plus minus a 4 ohm error because of the uncertainties in our measurements. And there you have it. That's how you do this lab, simulated, but in real life as well. Any other questions before we end off this recording? Once again, thank you so much for catching up on my errors because the numbers were just really far off. All right, but this is how you'd go through these type of problems here. So thank you for joining me, and here ends the recording. Bye now.